Okay, so we have seen work in the last class, and what we have seen that work can do, and so work is done by the gas in two ways. So when work is done by the gas, it is always expansion, and if work is done on the gas by some other agent, it is always compression work. So in that way, you can see that how much energy is received by the system or how much energy is given by the system to the other system. Here system only means gas, right? I think we have defined the various types of definition, like what is thermodynamic coordinate, what is thermodynamic state, right? So what is thermodynamic? Okay, we have also discussed thermodynamic equilibrium. Have we discussed thermodynamic equilibrium? I have discussed, but I think you don't remember.
So in the first lecture we discussed.
Yeah. So in thermodynamic equilibrium, it contains thermo and dynamic. Dynamic is from the mechanics, thermo is from the for this chapter, and it will have inherently the all types of equilibrium. So thermodynamic equilibrium means it must be in the mechanical equilibrium, and mechanical equilibrium means the net force is 0. Generally, we write the mechanical equilibrium for the immediate movable surrounding. Okay. So if you are solving numerical, and if you are supposed to write this mechanical equilibrium, you will write for the immediate movable surrounding. So in most of the cases, we are going to do it for the piston, right? The piston is the movable part of the engine. The cylinder is the static part. It will not move. It will not expand or shrink. It is made of a rigid body. So when you think of the mechanical equilibrium, you have to write for the piston, right? So I will mention this here. So generally, in mechanical equilibrium, we write for movable surrounding, and we take the immediate surrounding. So from the idea of work and theorem chapter, you can always think that how energy is or how energy flow is taking place. If you can understand the energy flow, then it's easy for you to write the equation. The second equilibrium we talk about is called thermal equilibrium. So thermal equilibrium is at every point within the system, the temperature is constant. So we have discussed this. Sometime you will come across, a gas separated by a piston. So you may have a cylinder. I mean, it's not cylinder, let's say some container, and it is separated by the piston. Okay. And then we have a gas on both sides. So this is called the closed system, and the behavior of closed system is that in closed system, we cannot transfer the mass, right? The mass will be constant. And a constant mass means what? What will be conserved here? The number of moles will be conserved in both the compartments, right? Even though the piston is movable, the motion will not affect the, tell me guys what?
Number of moles.
Number of moles. So when you're solving numerical of, closed container type, in that case, if you only conserve the mole, you will get the answer. So most of the questions which are based on the closed container type, separated by the piston, can be solved only by conserving the mole. But in that also the separation, the partition, the piston, the movable part will have two properties. So this could be of two types. Okay. So we need to understand there are something called types of walls. So how many types of diwar we have? So there are two types of wall that you should be aware of. The first is called diathermic wall. So what is diathermic wall? A wall through which heat can pass almost immediately, and therefore if a diathermic wall is the separator, it will always maintain the same temperature on the both sides at equilibrium. So I know as long as there is a chaos, we cannot say about what when the system will reach the equilibrium, the temperature on the two sides will be same. So how we define mathematically a diathermic wall? So a wall with a specific heat capacity is zero, or better you can say tending to zero. So what are the examples? So every metallic wall are diathermic wall. So dia means through, if you remember. Dielectric, if you remember. Hello.
Yes, sir.
So
Yes,
through
sir.
which dielectric means what? Through which electric field can pass. And
Yes, sir.
conductor was, in case of conductor, what we said that okay, through which the field cannot pass. So when I say diathermic wall, then a wall through which heat can pass easily, and the amount of heat absorbed by the partition by the wall will be negligible. So we can say that all heat exchange will take place between the two partitioned system. No heat will be absorbed by the wall. It is clear what I'm saying? Because the specific heat capacity is how much? Zero. So if you remember the formula from the calorimetric, ds equals to dq equals to dms d theta, right? Or ms d theta, I can say this way. ms. So to change the temperature by d theta, how much energy we need? dq. But if s tends to zero, what will happen? This will always come. Understood? So when s tends to zero, so by taking negligible amount of energy, it can make the change of temperature, and it will remain in equilibrium with the temperature of the immediate surrounding, which is gas here. So mathematically, a diathermic wall means S tends to zero, which means in such question, okay, diathermic. Okay, just I'll mention the meaning also. Diathermic. So when you are solving question like this, in which you know the wall is diathermic wall. So for uh, gaseous systems partitioned by diathermic wall will attain the same temperature on both sides at equilibrium. I hope this is clear. What is diathermic wall? What is the purpose when we use? So you can also add one more information. So most of the metals are diathermic. So metallic, piston will maintain, will act as diathermic. Okay. All right. So you should remember this. Generally, okay, not always. Now, most of the metal with higher electrical conductivity also exhibit the higher thermal conductivity, and that is a trend. So the thermal conductivity and electrical conductivity are proportional to each other. So that point is not required, so I can ignore. Let's go to the second type of wall. The second type of wall is called adiabatic wall. And the word adiabatic, if you see its Hindi translation, it is very interesting. It is called Rudhosh. Rudhosh means like if you know the Hindi word Virudh, against, and Ushma is basically meant for the heat. So it is against the heat. That is you can say the Hindi meaning. So a wall which is against the heat, which means it will never let the heat to pass through it. We call adiabatic wall. So any adiabatic wall cannot allow the heat to go on the other side. So it prevents the heat flow. So such wall prevents the heat flow through it. So if we have a adiabatic wall, then it is quite possible that within if we have a partition which is adiabatic in nature, and generally there is also a conventional way of showing. So we show it like this. In diathermic, the way of showing is we make a dotted diagram, and here we draw the lines, which means if it is adiabatic wall, then heat can't pass through it. Okay. So from either side, heat will not flow. So any heat given to the left will be part of left, any heat given to the right will be part of right. Of course, heat transfer can take place through the movement of piston. So you can do the work transfer instead of heat transfer. So the way to give energy to anybody is there are two ways. Okay, heat transfer and work transfer. Both are ways of giving energy. Sometimes you fail to give the heat, but you can give the work. So for example, let's say if a person is going to a restaurant and he has eaten a lot, and then he has no money to pay. So if you pay money, it's like a heat transfer. You're giving the heat. But if you don't have any money, then you have to work in his kitchen or somewhere else to pay the amount which you have consumed, which is very typical of the old Hindi movies. So that is like the work transfer. So you pay back using work. So energy flow can take place in two mechanisms. One is a direct heat transfer, direct energy transfer. Other is you don't give the heat, rather you do the work, and in that way you can transfer. So for adiabatic wall problem, how we attempt question when we come across problem in which we have the adiabatic wall and we have two partition. Interesting. So if piston will move from here to here, let's say, to give you the example, like how we attempt question like this, I'll take an example. Let's say I'm giving some energy to this. And as a result, what will happen? The piston is, let's say, moving towards right. Now, when the piston will move towards right, is it expanding? The left gas is expanding, isn't it? And the right gas is getting compressed. So the left gas is doing some work, yes or no?
Yes, sir.
So the way of writing question will be that Q given, okay. Now the heat current pass on to the other side. So Q given, out of this energy, I perform some work, let's call W1. And the remaining part I can use for changing my own temperature, my own internal energy. So we can say this is delta U1, the first compartment. But for the second compartment, it is not receiving any energy. So it is having nothing actually. So but it is getting energy by virtue of work. So work done by the first is the energy received. So that is like alternative way of receiving energy. So what you can say for one and for two, the W itself is the energy received. So when you compress it, you receive some energy, but you are receiving energy not in form of energy, you are receiving in form of work. Actually, this is called the work transfer. And this work transfer itself will help you in raising the temperature. So this is how it is happening. So this will be equal to delta U. So in this way, you can receive the energy. In this way, you can write the equation. See, first law, even if you understand, it's totally okay. If you don't understand, always think in a logical manner. That will help you in solving question faster, better, and with more accuracy. Many times I have seen that students struggle with, applying the formula of first law. I don't feel that there is a need to apply the formula. It is natural. It is so natural that it is so organic that if you understand what is happening, how the energy is coming, how it is going, you can just start the question and you're done. So most of the challenging problem you can do mentally if you understand the energy flow. Okay. So work is also energy flow. So when you do work, you give your energy to somebody else. When you get compressed, you receive energy from somewhere else. And the energy you're receiving is in form of work. Understood what I'm saying? Hello, guys.
Yes,
And
sir.
in case of this such system, eventually the final temperature we cannot say will be same or different. So it is quite possible that the eventual temperature may be different because the heat transfer is the wall is adiabatic, so it is quite possible to maintain two separate temperature on the two sides. It is quite possible. Understood? Hello, hello, hello.
Yes, sir.
So you have to think about all such questions logically. Now, if I have again a question in which we have an adiabatic wall, and then what I do is I also attach some spring. Then how we are going to write the equations? Okay, so let's say we have a container, and I'm taking the wall as adiabatic wall, so nothing can pass through the. Generally, when we design a system, then we make the wall adiabatic, and this adiabatic wall will prevent the heat to radiate outside. I mean, energy cannot escape the system. If energy will escape the system, the problem is it is difficult to write the equation, right? So we cannot write the energy conservation equation. So the outer wall is adiabatic by default. I mean, I'm taking this as adiabatic. And the partition is movable and adiabatic. Now imagine if the outer wall I make diathermic, what will happen? If I make the outer wall diathermic, then the surrounding will decide the temperature of the system. The atmosphere temperature will be the temperature of the system, isn't it? Because can we change the temperature of atmosphere?
No, sir.
It means we have to be in equilibrium with the atmosphere no matter what. So imagine now I have a partition. So now I have a partition which is also adiabatic. And then what I do is I attach some spring. Both these springs are in the natural And then what I do is I give some energy. Once you give the energy, the gas in the left compartment will try to expand, and the piston will move slightly towards the right. So who is losing energy by virtue of work? The left compartment gas or the right compartment? Which gas
Left one, sir.
which gas will do the work transfer?
Sir,
the
the left
output?
one.
The left one. Okay. No, the work is only depending on how much you expanded, isn't it? So whatever work the first is doing, that work will actually go to the, you are doing the work on the piston, but the piston will give energy to whom? Piston is going to compress and elongate two springs, isn't it?
Yes.
Understood. So there are three types of energy consumption. Of course, one is so first gas is expanding, so it is of course doing some work. The work is done on the piston. Okay, piston is not keeping any energy. Piston is not keeping any energy, so this energy must be going somewhere, right? Piston will come to rest eventually. It means it is having zero energy. So where the energy given to piston has gone? Tell me. Where the energy of piston has
To
gone?
both the springs and the other side of the gas, sir.
Yeah, so some energy is received by the right compartment gas, because you're compressing it, so you're giving some energy, isn't it? Now, when we know that how much gas has expanded, and if we know the process also, we can exactly write that how much energy is consumed. But right now, what we can say, like what is in our capacity to write? For the left gas, what we can say? For left gas, you receive energy Q, okay? And as you receive the energy Q, you do some work. Now, here it is interesting. It's difficult to write the work done by the gas, because the gas is giving energy to the piston. Piston is, of course, giving energy to the two springs and also compressing the gas. So there are three types of work. The third is unknown. The third is unknown. But if I take the entire system, if I take the entire thing as one system, then what is happening? Then we can say something. Out of energy given Q, how much energy we kind of is stored by the springs? Sorry. So can you see that the two springs will store this much energy? Now I am talking about the entire system. How much energy I gave? I gave Q energy to the entire system, left and right together.
Yeah.
So here, when you see that things are difficult to write for one part, we write for the entire part. So out of Q energy, this much energy is consumed or stored by the spring. So what will happen to the rest of the energy? The rest energy will change the internal energy of both the system, which means this must be equal to what? See, work part is done. I mean, work is gone, because for the entire system, the energy given is this much, the energy kept by the spring is this much. Rest of the energy will do what? rest of the energy will change the internal energy of system, and therefore we can write this as delta U1 plus delta U. Do you realize this equation, how I'm writing?
Yes.
Now, why I'm writing the way I'm writing? The answer is we do not know what is happening to my work. Okay. In the previous example, if you look at it, the expansion of gas is directly giving energy to the gas itself. So we know that this work is only gas, isn't it?
Yes.
Sir,
Yes, yes, sir. Tell me.
sir, so like when we are giving Q amount of heat to the one side of the gas, sir, it will do some work on the spring and hence increase its energy. So some part of it will go to the spring.
Yeah.
And the other part, the remaining part which is lost by this compartment of gas will be like
Yeah.
all of it will be transferred to the other side, right?
So
sir?
yeah, so the change of internal energy of both the compartment will get energy from there only, right? See, it means if I'm having some saving amount, if you, I mean, the left compartment and the right compartment say that, see, I have saved 10 rupees, I have saved 20 rupees, and I gave how much? I gave 100 rupees. Okay. So out of 100, some energy went to the K1, some went to the K2. So whatever is the saving of the both will come from the difference only, because energy is conserved.
Yes,
My change in saving amount will be due to what? Due to some incoming energy, isn't it?
yes, sir.
So if I receive Q, I mean if the system received Q energy, half K1 x square went to the first compartment, half K2 x square went to the second spring, then remaining energy will do what? The overall gas has not expanded. We haven't compressed the atmosphere, right?
Yes, sir.
Okay. So in that case, we can say that remaining energy will change the internal energy of each system separate.
Yes, sir. So like U1 and U2 will like cancel out each other, right, sir?
So delta U1, delta U2, I mean, no, it will not cancel. We don't know about it. So some other, parameters will be given to you, which will help you in calculating the value. So they will give you something. They may give you temperature, they may give you displacement, they may give you something. I mean, of course, the number of variables and the number of equation will be always equal. So here I'm giving only one part of it, that how to write the energy relation. Okay, so what I'm writing here is energy relation. If you want to go back to the original method, do you remember the way I told you? Draw the ABD
Yes, sir.
or piston. If you draw the ABD piston, after X compression, this side pressure is P1. This side pressure is P2A. Isn't
Yes,
it?
sir.
This will pull by K1X. This will push by K2X.
Yes, sir.
So what is the net force acting on this?
Mm,
Or what is the difference of pressure? So you can say P1A equals to K1X plus K2X plus P2A.
yes, sir.
If you go that way, which is called the mechanical equilibrium, that is what we have to assume. If it is a well-defined process, then this will be followed. So what we get is P1 minus P2 into A equals to how much? It is K1 plus K2 into X. Isn't it?
Yes, sir.
So P1 minus P2 is, of course, I mean, you can add like this, K1 plus K2. So the work done by the gas, the first gas is doing the positive, second gas is doing negative work. What is the net work done by the system? So you can say P1 minus P2 into dV
Yes, sir.
by both system. I'm not one system. Okay. So this will be how much? This integration,
Yes, sir.
which you can add as K1 plus K2 by X, and dV is A dx.
Yes, sir.
So the total work done by system is how much?
Half K1 X. Yes, sir.
Which means out of all energy, this much consumed in work, right?
Yes, sir.
So with the remaining energy, what you can say, that will change the internal energy of the entire system, isn't it?
Yes, sir.
Are you getting it what I'm saying?
Yes, sir.
The way to see, if you want to solve in the more lengthy way, like step by step, like how to think from scratch. So there is one way. So for left,
Sir, and no, sir, by the intuition way, like there is no energy exchange with the surroundings. So how
yeah,
is there a change in internal energy of the entire system?
because I'm doing work, so I'm losing energy. So my energy will change. I may lose it. So the delta U1 may be negative. I don't know whether it's negative or positive because I'm also receiving energy. So we write delta U1, which is N CVDT, and then the equation will give me whether it is positive or negative. I don't know.
Okay, sir.
So delta U1 may be positive, may be negative. So
Yes,
let's
sir.
say if I have some energy and I'm spending it, so I will lose energy. So delta one U1 will be negative. I did some work, I received some energy, and the work which I did was less than what I received. So my internal will grow. So the math will take care of everything. I mean, we should not be worried about the same.
Okay, sir.
But if someone wants to do one by one, it's a system by system. So you have to write the kind of first law for each system. For the first left gas, energy received equals to work done by the first gas. What is work done by first gas? P1 dV. Can you write like this? Work
Yes, sir.
Yes, sir.
and delta U1. Correct?
Yes, sir.
Now, what about the, okay, now the first is work. I mean, you're pushing the piston will, I mean, do some work. Now, what is happening to the right compartment? So the left compartment has pushed the piston, has performed this work. So you gave this energy to whom? You
Right.
gave
Okay.
To the right
no,
compartment.
no, you gave to the piston actually. Your interaction is with piston. But piston,
Yes.
pulled the spring. And this is the energy received by the right compartment, isn't it? So
Yes, sir.
this is like a cue for the right compartment. But this is the work transfer. This is the work transfer, right? So this must be equal to what? Tell me. So the energy you are receiving in this format, in terms of heat transfer, in terms of work transfer, then it is also doing some work. How much work? P to dV, which
The
is of course going
piston
to be
is doing work on the
gas.
gas. Yes, sir.
Yeah. So now the first piston is doing some work on the gas, and then gas is also doing some work. Of course, it is getting compressed. So this must be the delta U2.
Yes, sir.
Now, if I rearrange these two equations, can you get the same answer?
Yes, sir.
Just check. So just the first is giving, it is doing the work, and this is changing internal energy. The second will, so this much work will go to the piston directly. And piston will consume this much energy. And the P2 dV,
Sir, the P2TV is not getting cancelled out.
I mean, this thinking. So the work transfer, the work given to this. No, this is actually, this is this term will not appear as it. This will not appear. Why? Why this will not appear? The reason is the first piston is compressing, and all of the energy received by the second system will change its internal energy. The P2 is not required as well. This is the work done. Out of this work, this much energy is consumed by the spring. The remaining energy will, this remaining energy will go to the second gas itself, isn't it? And therefore, if I add these two equations, what we're going to get? This gets cancelled. So
Yes,
are we
sir.
getting the same answer?
Yes, sir.
So this is how we can do, of course, one by one. So this is for the right compartment. The work done by the first gas on the piston, out of that work, the piston will give some energy to the these guys, the spring, and then the remaining energy will go to the right gas itself, and that's why the change in internal energy of that gas is this much, isn't it?
Yes, sir.
So again, this way we can also get the same answer. Or if you write for the entire system at once, then the total work done by the entire system is also coming equals to half K1 plus K2 into X square. So Q minus the work is delta U1 plus delta 2 U2 of the entire system. So these are the ways of thinking. And what question you are seeing right now are the most advanced problem of JEE advanced. I mean, these are most advanced problem of this first law of thermodynamics. These are not easy problems. These are the most advanced. Okay. So the wall problem you understood. How, I mean, when you will see the question, you will understand. It's not difficult, but this is how we think about the wall problem. And when they mention the process, that what thermodynamic process is happening, then it is further easy to write the question. So this part you understood, the wall types of wall is clear to all of you?
Yes, sir.
Yes, sir.
Sir, the P2 dV, like why it's not considered, can you just tell again?
See, the gas is getting compressed, so it is receiving energy.
Yes, sir.
So which is equivalent of saying that because you are receiving energy, so with that received energy, what you will do?
Change the internal energy of the system.
Exactly. So that energy which you are receiving is changing your energy because you're not doing any work. You're not giving to anybody else, right?
Yes, sir.
So the work itself is with the way to receive. Okay, the way of thinking, you see, the way you can think is this way, that maybe I can think in this way. Let me see.
Sir, it's like the centripetal force.
Yeah, I mean, for second system, what is the energy received? What is the Q value? 0.
Yes, sir.
What is the work done? P2 dV
Yes, sir.
and delta U2.
Okay, sir. Sir, the P2 dV is the delta U2.
Exactly. The P2 dV is this value. I mean, the first question will be the P2 dV. Okay.
Yes,
So this will take care of everything. Okay.
Okay, sir. Yes, sir.
Next. The third equilibrium we talk about is what is called? The mechanical and thermal. What is the next equilibrium? We have discussed this.
Chemical equilibrium.
Chemical
sir.
equilibrium.
And chemical equilibrium means the composition of system is constant. So that will give you that, okay, the moles are conserved. So that's why we say the moles of constituent gases is constant or conserved. Because if there is a reaction happening, then the component will change, right? One will convert into other form. So there is a continuous change of composition, and that's why it is called chemical equilibrium, which means the rate of forward reaction is same as the rate of backward reaction. So of course, this is not, I mean, we are not supposed to, concern about this. Now, let me give you the other definition. This is the meaning of thermodynamic equilibrium. Now we'll talk about the types of system. I mean, I should have discussed this before, but anyway. Types of system. How many types of system you are going to deal with in this chapter? So the first is called open system. So what is open system? A system which can do the heat transfer as well as mass transfer. The mass means the composition, whatever it is containing, that can also be sent out or can be taken in. And heat can also be taken out and taken in. So a system which can transfer heat as well as mass is called open system. So we can say in short, heat transfer plus mass transfer both can take place. So nowadays it's a winter going on, and I think you all must be using the geyser for some reason. Okay. So in geyser, if you look at the geyser, this is a very famous question of calorimetry also. In geyser, what we have? Inlet and outlet, right? So it will have water. It will have some the coil system, some heating mechanism, you can say. The cold water will enter, right? So the cold water will enter from this end, let's say, and it will enter at temperature θ1. And after getting heat from the coil, the water will rise, the hot water will come here. And when you receive the water from this side, what you get is θ2. So if I think the geyser as one system, then a geyser represents which system? It represents open system, right? Because the mass is also coming inside and going outside. The water is mass, right?
Yeah.
And it is also coming outside with a different temperature. So it is also taking heat away from the heater, isn't it? Hello, hello.
Yes, sir.
So if I say dm is the mass entering the geyser and dm mass is coming out of the geyser, then how much energy it has gained while going from bottom to the top, from inlet to the outlet? How much energy you have received? So the energy received is how much? Mass is specific heat of water into
Q2
d
minus
theta.
theta.
Okay. So a heater will have the specific way to, I mean, specific power to deliver heating process. So the dq by dt is how much? Dm by dt is called the mass flow rate. So depending on at what rate the heater can supply the energy, if you open the valve or the tap, to its full extent, the heating effect, the θ2 will be not very high compared to θ1, right? But if you decrease the rate, because this is constant, what heater can provide is constant, isn't it? So when you go and buy a geyser, it comes with a fixed rating. It's a 2000 watt heater, it's a 2500 watt heater, okay, or maybe 3000 watt heater. So 3000 watt heater means what? It can only provide you how much? 3000 joule per second, isn't it?
Yes.
So that is kind of constant, no? I mean, if you give too much water, will it be able to heat it to the right temperature? So if the inlet water rate is very high, I mean, the thing is you won't get very hot water. So you have to make the rate at a speed which can give you the desirable temperature. So that's why you have to adjust the hot and cold opening, right? This is what you do, the actual engine at home in winter. Now those are homemakers, they don't know what is winter, but anyway, there is something called winter. So dq by dt is how much? dm by dt s theta 2 minus theta 1. So in fact, this you may come across question on this, but a geyser is a very nice example for the open system. Okay. Now in this chapter called thermodynamics, we are going to deal with which system? Open or closed?
Close.
So luckily we are going to deal with only closed system. So what is closed system? What is closed
So
system?
mass transfer is not there.
Yeah, so of course you can give heat, but you cannot, do the mass transfer. You cannot add something externally as you wish. Okay. So generally we have a closed system, and the piston cylinder arrangement. Of course, we do have an exhaust also, but that is a different. I mean, when we do the process, the exhaust is called the last stage of engine. So engine will have a typical engine will have the 4-stroke engine. The 4-stroke means there are 4 steps actually. And that typical engine we are also going to study in our syllabus when we study the Carnot's theorem. So if we have a piston cylinder arrangement, then typically the gas cannot escape unless we open some valve and let it go. That's called exhaust. So when you give energy, of course you have a mechanism to give energy. So this is called the heat transfer. But what cannot be transferred is the mass transfer, right? So mass cannot be transferred here. Understood what I'm saying? So in closed
Yes.
system, only heat transfer. Can you guys tell me what is heat transfer? What is heat by the definition?
Sir, it is the transfer of thermal energy.
In fact, sunlight is also having some thermal energy. Can we call heat transfer?
No, sir. Sir, we can, right?
So what is the definition of heat transfer? Like how you distinguish that this energy is heat energy and this energy is not heat energy? And what do you mean by thermal energy? Like,
Sir, when like the kinetic energy of the molecules increase,
yeah.
that time we can call it as heat energy.
So if you compare, if you compress the piston, the kinetic energy of the molecule may increase. It will increase, in fact. Can we say this as heat energy?
No, sir.
Okay. So there must be some, if you are saying different name, there must be some differentiating characteristic, isn't it? We are not saying something heat just because we want to say it's not fashionable. So it means there must be some inherent difference in the mechanism. Energy is universal. And the different categorization, classification that we have done is because of a different mechanism. Okay. So let's say if you want to give money to someone, you can do the, in cash transfer, you can do the online transfer. You can go to bank and deposit the check. You can write a draft also. So money is the same, but there is a different mechanism. And therefore we have different name. It's online transfer, it's cash transfer, it's a check transfer. I mean, there are many ways in which you can give or take. So how we differentiate the energy which we call heat then compared to the other energy form?
So
Because
heat,
energy is energy.
yeah, I
Yeah,
think
tell me.
heat will lead to maybe phase change, state change, sort of.
No, I can do it by other way also. Okay, so if you press the ice, it will melt. Do you know this?
Yes.
And that is how the In ice, it's
Sir,
getting the same thing happen with thinner edge, I mean thinner bottom. You create a very high pressure which melts the ice, which will act as a lubricant, so you slip. And the moment you go next, the ice will refreeze. That's called the renegation of property.
sir.
Yeah.
So, like heat is the transfer of energy by the mechanism of initiating a temperature difference between two
Exactly.
regions.
That is the answer. That is the answer I was looking for. So it is the energy transfer by virtue of difference of temperature. There's nothing else. If the energy is getting transferred by virtue of difference of temperature, whether it's a you can take a rod, you can heat one end, the other end will get heat energy. I mean energy automatically, because the difference of temperature is the cause behind the energy flow. So that energy flow, which is happening by virtue of difference of temperature, we call heat. Okay. So when you say that you are giving Q, you're giving through the mechanism called the temperature difference. Okay. So you may insert a rod and you heat the rod on the left side, the heat will reach the gas automatically. So any mechanism in which the temperature difference is the cause behind the energy transfer, that mechanism is called heat. So that is the actual definition of heat also. So you can define the heat. What is heat? This is very important. And we are learning this chapter, we must understand the heat. So heat is, of course, one of the method, one of the mechanism, one of the way by which energy is exchanged. There are many other ways. So work is also energy exchange mechanism. All are the energy exchange mechanism, but because of the inherent difference in the mechanism itself, we have given different name. But the end goal is same. Either you give energy, you take energy. That's it. So when you touch an ice, what do you feel? You feel cold or hot?
Cold.
And why you feel cold?
Because its relative temperature in comparison to our body temperature is quite low.
Because you lose energy. The direction of heat flow is from your body to the ice, isn't it?
Yes.
So the difference of temperature of the ice and your body will let the heat flow to establish. And because the heat flow will depend on the difference of temperature, the faster, the more the difference, the faster the flow. So if you touch something really cold, you will burn actually. It's they called cold burn, isn't it? Or you can say
Yes, sir.
there's something called frostbite also.
Yes.
So earlier we used to, for the swelling purpose, we used to have the hot water. We used to, put the hot water in a thermos and you give the massage. Okay. Now you can, doctor says, okay, you can use ice also. Because whether you use the hot water or you ice, the heat flow will take place in both cases. The only difference is the direction of flow, isn't it? So if you
Yes.
want that energy should come from within your body to outside, you can take the ice. And what really matters is the flow of heat. Okay. So you can use ice bath also, you can take the steam bath, you can take the, thermos with ice, you can take thermos with hot water. Both will have a similar effect. The only difference is the direction of flow. So heat is, it is energy measured in transient state due to and okay. So first of all, it is energy measured in transient state, and it flows due to difference of temperature. So is there any way to know that how much heat your body having? The answer is no. We cannot find the absolute heat content of any body. So what we can actually find? The transferred value. So heat is only measured when it is getting transferred. Heat cannot be measured in a body, that how much heat a body is having, that cannot be measured. Understood?
Yes, sir.
So heat is only measured in transient form, which means while it is flowing, you can find how much. So let's say when you touch the touch the ice, there is a flow of heat from your body to the ice. And let's say if you melt the entire ice, I can clearly say that the energy which has flown from your body to the ice is m into L. Can we say? L is the latent heat of fusion.
Yeah.
But does it mean that I know that how much heat you have?
No.
Or does it mean that how much heat you have given or has flown from your body to the ice? What does it mean? The flow part or the absolute part which you have?
The flow.
Flow part.
So heat we cannot measure. The absolute heat content of a body is immeasurable. What we always measure is the flow, the transferred value. And when we say the energy as a heat, it is redundant to call heat energy. Heat, the word heat itself means energy flow due to difference of temperature. So saying heat energy like energy flow energy. I mean, anyway, but in general conversation, we also use the word heat energy. In fact, heat is sufficient, but it's okay. So heat is a form of energy. What is work? So if you have watched the lecture of work energy power, if you have studied work energy power, the work is also a mechanism by which you either give energy or take energy. So when you do work, you give energy to someone. When you receive work, you receive energy. And the difference is here the force is involved and here the displacement is involved. So when the point of application is getting displaced in the direction of applied force, then we say that some energy is getting transferred. Okay. If the force and the point of application are not moving in the direction, if it is mutually perpendicular, we say there is no transfer of work. So work is also energy. So these are like the, you can say, the outer cover. Okay. Inside both are doing the same job, energy transfer. Okay. And that energy you can use for any purpose. So you can use heat also for the purpose, you can use work also for the purpose. In situation where the heat transfer is not possible, we can do the work transfer. So for example, if I have an adiabatic wall everywhere, the piston is also adiabatic, I cannot give heat energy. I mean, I cannot give heat actually. But I can still push the piston. No? I can apply the force on the piston, I can push it, isn't it? And when I push the piston, then what I'm doing? I'm still giving energy to whom? To the piston. But now I will say I'm doing the work on the piston. And the problem is because we are not able to see the energy, we see work and energy in two different things actually. So in general, most of the students, they think, I mean, they always see them separately. They think work is something and energy something. The reality is work is a mechanism, a way. So if someone will ask you, what is work? So in the very first lecture, I always say, work is a way by which we transfer energy. It is one of the mode of energy exchange. In this mode, of course, force is involved. In this mode, some sort of displacement is involved. And because the involvement of different physical quantities is there, we call by a different name, and we use the word work. In heat, the energy flow is not due to the force or displacement, it is due to the difference of temperature. So you touch the ice, energy has gone from your body to the ice, and it will not ask you. Will it ask you? Should I go or not?
No.
It will start happening, no? Because the temperature difference is the cause behind the flow of energy. Understood what I'm saying?
Yes, sir.
Okay, anyway. So in closed system, only heat transfer can take place. Okay. Mass transfer. So only heat transfer, no mass transfer.
No mass transfer.
Okay, in a closed system, can we do the work transfer? Can we do the work
Yes,
transfer?
sir.
So what is the criteria to do the work transfer? Like what kind of system is capable of doing the work transfer? Any system with a movable boundary can do the work transfer. So when work transfer is done, for those systems with movable boundaries, let's say if you have a gas filled in balloon, can we compress the balloon? Can we compress the balloon? Yes or no?
Yes,
Sir,
sir.
if the balloon is tied up, then
Yeah, of course, balloon is filled with air and there is a, you have tied the opening.
all right, still we can compress it.
We can compress, no?
Yes, sir.
So the boundary of the balloon is moving. So when you compress
Yes.
the balloon, what you do? Which kind of transfer you're doing in terms of energy? You're doing the work transfer, which you don't realize in general. Okay. So when you compress something, expand something, when there is a boundary which is moving, any boundary means a system is a gaseous system is confined in a boundary and you're moving the boundary. Such a motion of boundary is actually an example of work transfer. Okay, because I have told you that work is a boundary phenomena, and when we say that there's a boundary is moved against some resistance, the work is being done. Okay. So work transfer can happen with any kind of system. The only criteria is it must have movable boundary. Understood?
Boundary.
So if I give you a a glass jar, if you give a glass jar and the lid is also tightened. Okay. The gas in the glass jar is which system? Open, close, or what? So the gas is packed in this this glass jar. It's a hard surface. So can we move the
Right.
boundary?
No, sir.
No, sir.
So what kind of transfer is not possible in a glass jar?
Work
Work
transfer.
transfer. Can we do the mass transfer?
No, sir.
No.
Means it is
No,
closed
sir.
system. It means it is closed system.
Yes, sir.
But if you put the gas jar in a sunlight, the gas will get warmer.
Yes, sir.
Yes, sir.
So if the surrounding is at a high temperature, the heat will flow through the glass also, isn't it? The heat will flow through the lid also. Let's say the lid is made of tin, isn't it?
Yes, sir.
Yes, sir.
So what transfer is happening? It is the heat transfer. The energy is flowing because of the difference of temperature on the two sides of the glass wall. So a jar is an example of a very nice example of closed system, as well as a fixed boundary system. And therefore, such system we call what do we call? Their third category.
Isolated.
Yeah. No. But glass jar is not isolated because for isolated system, what is the condition?
Sir, heat transfer is also not.
Yeah, heat transfer is also not possible. So you have to take the thermos flask, this the fixed temperature flask in which you keep the hot or cold water, and it keeps it cool or hot for a long time, right? So
Yes,
there
sir.
nothing can move. The mass cannot move unless you don't open it. The heat also cannot flow. So the glass jar is a unique number. In that case, it's a closed system, and because I'm fixing the boundary, so the work transfer is also not possible. In isolated system, what is possible? Neither heat transfer nor mass transfer. So the definition of system is only based on the heat and mass. But if I ask you another question, that is it possible to transfer energy through the work transfer for isolated system? Is it possible?
No.
Can we transfer work?
Yes, sir.
Yeah, we can transfer. Why? Because the boundary can be moved, right? I can press the thermos. It's less a made of rubber. So we can press it, isn't it? So when you press it, the temperature will increase or decrease.
Increase, sir.
So you can put a cold water in a thermos and keep on pressing it forever, like maybe for 1 hour, and you can measure the temperature. We'll find it's a hotter now. Yeah, you can do this experiment at home. So you can see that the work transfer is giving energy to the water inside the thermos. I mean, the rubber thermos. Have you seen that rubber thermos? You might have seen. You might have used also. So you can do this simple experiment at home. Okay. So these are called the system type. I mean, you should understand that what is closed system, what is open system. A closed system may have, I mean, may not have, or may have mass. I mean, sorry, a closed system may or may not have work transfer, right? So a closed system with fixed boundary cannot have work transfer. A closed system with movable boundary will have work transfer. Understood?
Yes, sir.
So if I say that a process is isochoric, I hope you have heard in chemistry, at least in thermodynamics. A process is isochoric. What does it mean?
Sir, no work.
Volume remains constant, sir.
Which means I will say the boundary is fixed.
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 So if the boundary is fixed, then which kind of transfer will not take place?
Work.
Yeah. So for in isochoric process, there is no concept of work transfer. So the relationship between the heat given and internal energy change is the only relation which is possible for such process, isn't it?
Yes, sir.
So we'll see the process very soon. Anyway, so this part is clear. What is isolated system? So I can put a kind of case here for closed system. Work transfer may or may not take place. For isolated system, work transfer may or may not. Again, it depends on how the boundary is designed. So these are the simple and definition which one should be aware of. So system is clear.
Yes, sir.
Okay. So now we'll talk about the thermodynamic process. So what is thermodynamic process? What is thermodynamic process? Okay, let's say if you go from your home to your friend's home. So how many coordinate points, how many longitude and latitude you will touch while reaching your friend's home?
Infinite, sir.
Infinite. Is it possible to go from the one coordinate to another coordinate without traversing the intermediate coordinate?
Not yet.
Okay. So unless there's some time travel, okay, you may just vanish from one place and appear in other. But I think it will go through the space-time curve anyway. Now the idea is a thermodynamic process is all about changing the state of a system, right? Any gaseous system. And what you do is you either change pressure, you change volume, you change temperature, you change any combination of the three. You change the internal energy, you change the entropy, you change the enthalpy. But is it possible to change only two values, like you go from P1 to P2? So between P1 to P2, between P1 to P2, how many P's will come? How many pressure will come between P1 and P2?
They're again infinite.
Again infinite. How many volume term can come?
Infinite.
We don't know.
Infinite.
We don't know. It may be a constant volume, so it's only one answer. So if I'm saying that a gaseous system is going from P1 to P2, then I can definitely say at least for pressure, it must have infinite values, right? So a thermodynamic process means a gaseous system at one state is going to the another state through infinite intermediate states, such that at every instant the thermodynamic coordinates, or you can say the thermodynamic variable, or you can say the thermodynamic system is at equilibrium, and so its variable is well defined, its coordinates is well defined. So when we say a process, it means it will go from one state to another state through infinite intermediate state, such that at every state, the thermodynamic variables are in, the thermodynamic system is in, or the system is in, you can say, that's better way of saying. The system is in thermodynamic equilibrium. So everything is well defined. So you know P1, you know P2, but you also know the P in between. And for such system, we plot graph. A system in which things are not well defined at intermediate position, I cannot define the graph. I cannot show it. I cannot represent it that how it is going. Okay. So let's say you are moving in a racing track and the track is having sensor. Suddenly you jump out of the track, go to some countryside, and then you again come back after traveling 1,000 kilometers or 100 kilometers back to the same track. So your location, the last recorded location is there, but the rest of the location is not defined because there is no fixed path. You're just moving randomly. Okay, so there is no well-defined path. In such case, we call random process. So thermodynamic process will maintain the equilibrium at every instant, but a random process cannot maintain the equilibrium at every instant, but the initial and the final state will have equilibrium. So when you start solving question of thermodynamics, you will come across two types of question. One in which you will be given initial state, you will be given the final state, and nothing will be said about the process. That's very dangerous question, but very easy. When you come across a question in which the state, the process is not defined, but the initial and final is mentioned that is at equilibrium. To solve such question, we only use the energy relation between the initial system and the final system. We don't do anything else. We don't write any equation like the equation of process P1 equals to P2 B2 and so on. Okay. So whatever equation you write in gaseous state, in chemistry, those equations are actually meant for the thermodynamic process where things are well defined, where every instant the equilibrium is maintained. For end-to-end question, like a question in which you know the end condition, but you are totally unaware of the intermediate condition, there is no equation. And to solve such question, we only rely on the energy relation. And of course, PV question RT you can write for the initial state, because at initial PVT is in equilibrium, so you can write it down. You can also write for the end because there also they are, the system is at equilibrium. For rest, you cannot write anything, and therefore there is no mathematical function. So the definition goes simple. I'll just define the definition here. So when a system, I can say gas system, maybe liquid also. I'll just keep the gases only system. goes from one state to another state such that it maintains thermodynamic equilibrium at each, you can say at every instant. That's also fine. Then such process is called thermodynamic process. Else, what you call?
Random.
Okay, so else we call random process. I mean, only for thermodynamic process we define something called equation of state. It means state will follow certain mathematical equation. It means the variation of the state will have very well-defined path. So for thermodynamic process, we define equation of state. Okay. We can also draw, or you can say plot, graph between thermodynamic variable called indicator diagram. Okay. So these things are only for the thermodynamic process. So you can define for thermodynamic process. I hope you are getting what I'm trying to explain. It's not so easy, but if you can understand this part, you can master this chapter. So the indicator diagram is basically the graph part. Okay, how you plot the graph. Because we have too many coordinates, so graph is basically 3-dimensional. Sometimes it goes to 4-dimension, which we cannot plot. So we have the restriction up to 3-dimension. So we have PVT graph. We plot a 3-dimensional graph, and then we take a projection to convert the PV, PT, TV graphs. Okay. So you can also see 3D graph. I'll show you somewhere. I'll send you some pictures of 3D graph, how it looks like. So the process is clear to all of you guys?
Yes, sir.
Yes, sir.
Okay, so now we talk about the types of. Okay, no, not types. We first talk about the what is first law of thermodynamics? Are you guys there?
Yes, sir.
Yes,
What is first law of thermodynamics? And why it came into picture? So in the very beginning, you can say physicists were not aware of the fact something called internal energy. I mean, they never believed that even a system can also keep energy or store energy and can give back if required, can store extra value. So the first law actually talks about that in a cyclic process, for any closed system. So for any closed system in any cyclic process. What is cyclic process? The system returned to the same state from where it began. Understood? So for any closed system in any cyclic process, the net heat transfer is equals to net work transfer. Which means if you have a closed system, if it is cyclic also, then at the end of the process, whatever heat you give, you will derive the same work. It's like 100% efficient system, which will of course going to fail in future, and we will have the second law. So people were only aware of this fact that in a cyclic process, if you have a cyclic process, then whatever heat energy you supply, whatever heat you supply, it is going to perform the same work. So the total work is the dQ and dW for the cyclic process is always same. So this is the actual statement of first law. Now, because now we know, because the internal energy depends on the state. So if you go back to the same state, then the internal energy before and final will be same, isn't it? Hello guys, tell me.
yes, sir.
Yes,
So,
sir.
for,
Yes, sir.
so can we say for any cyclic process, the change in internal energy must be zero?
Yes, sir.
So because of this, I mean, these itself, these are all properties which you can use for the cyclic process. Let's say if I give you cyclic process in which you know the due for the two, I mean, let's say it's a 3-step process. And somehow you know the due for the first two process. The third can be determined, isn't it? How? The sum must be zero. So if a cycle is only having 3 steps, and if you know the due for the first 2 steps, can we determine the due for the third step?
Yes, sir.
So we have to use the below relation, the relation number 2, right? You will also come across a question in which you could find the dQ or the energy or the heat transfer for one of the given state in a cyclic process. So the RHS is somewhat easy to determine using graph. You know, if you know the PV graph, we know that area and the graph gives you the total work, right, in a process. So the right hand side, the RHS is somewhat very easy to calculate if graph is given, the PV graph is given. And let's say if I create a cyclic process with 3-step process, you know the dQ for the 2 process, you can find the dQ for the third process without doing any calculation. So I'll show you one example, which is very tricky one. Now, this is the law, first law, the way it was defined. And the purpose of first law is to define the internal energy. Yeah. Now, what does it mean? If a process is not cyclic, if you only talk about one of the process, not the entire cyclic process, you choose one of them. So dq is dw. So dq minus dw is how much? 0. So we know 0 can be replaced by du. Now just drop the integral sign. Can you say dq? So this equation is the again first law, but not for cyclic. It is for any elementary process. So even if you go from one state to its immediate next state, this can be applied. So this equation is in general too. So we say amount of heat given is work done and changing internal energy of a gaseous system. And this is applicable. This is for all thermodynamic process. This is applicable for all thermodynamic process. If you know the thermodynamic process, you can always apply this relation. The cyclic will not include the du for the obvious reason, because in a cyclic process, it is always 0. So first, I would like to show you the application of the first this relation. So for that, you should know the process itself. Let's say I draw a graph, PV graph. Look at this graph. You go from A to B, you go from B to C, and go from C to A. We all know that A to B is which process?
Isobaric.
Very good. So we all know A to B is isobaric. We all know what is B to C?
Isochoric.
Isochoric. But do we know what is C to A?
No, sir.
No, of course it is thermodynamic process, but it is not known to us. It's like some struggling actor, not a very famous one. The A, B, and B, C are some celebrity process, and CA is a process which is in the making. Okay, it's not known to the world, but it is some process. And because the standard answer, we are very much, we know how to solve the standard question. So I can write a very easily the dqab. I can write easily. What is dqab? It is isobaric process, right? As you said. So can we say this is NCPDT?
Yeah.
So I will not write DT, I will write TV minus T. We are not doing calculation. I'm just showing you how we think and how we write. Now dq to C is which process? Isochoric process. And for
Yes.
isochoric process, we know the formula is NCVDT. And then we have no clue about C2, right? Isn't it? This is like unknown. Now there are two ways in which you can solve. One is first find the process itself, then use something, and we get the answer. I'll show you that also later on. But we are trying to understand the application of the definition of first law of thermodynamics. So if I call this is P2, if I call this is P1, if I call this is V1, this is V2, can we find the area under the curve? So what is the area under the curve? Tell me, guys.
Half into P2 minus P1 into V2 minus V1. Sir.
which means the entire dW we can get it at once, half into V2 minus P1 into V2 minus V1, right, guys?
Yeah.
And also it is clockwise, so it must be positive, as we discussed in the last lecture.
Yes, sir.
And we know one fact that the dq in a cyclic is same as dw in a cyclic. The RHS is easy to find. And the LHS I can break into 3 steps. I can add dq, A to B, dq, B to C. I mean, of course, you can add delta Q, but I always prefer to write dq element form, because you never know that you sometimes you need to integrate as well. Because of this simple first law definition, do I need to calculate anything rigorous? No. Because I know this answer, I know this answer. Can you find this answer?
Yes, sir.
And you know the way of solving, right? How to get the third answer. So you should know that this is useful in many examples, in many situations. So I have given you situation where the first law definition is used directly to find the unknown value, especially the dq unknown. The work is something which is very simple to calculate, and in such situation we always choose this approach. I mean, of course, I need to go to the very basic of deriving it. Right? What is the CA? You can do so that way also, but it is simply very lengthy, and you will think that this question is a challenging question. So a question can be challenging and can be easy depending on how you approach the problem. And in thermodynamics, because it's a very intuitive chapter, I would say it's a very organic chapter, similar to the work energy power chapter. So if you can see the intuition, if you can understand the definitions, you can get the answer. Okay. So the cyclic was this much, but for not cyclic process, if you write for the process, the difference will have some value. And this sum was actually kind of mystery for a very long time. And of course, now we are writing this du, we know the KTG, but at that time there was no KTG, right? The Boltzmann was not even born when Sadi Carnot designed the engine. Okay, I think so. I mean, I need to check the date of birth. I may be wrong sometime. Let me check the history of Boltzmann and Sadi Carnot. So, birth date of Sadi Carnot. So Sadi Carnot is 1796. Okay, that's Carnot. 1844. So one thing is clear that the Sadi Carnot gave the idea of engine much before the guy was born. Which guy? The KTG guy,
Boltzmann.
the Boltzmann, right? Okay, so what I said is correct. I mean, I should be technically also correct. And that time, of course, the whole idea of internal energy was not there, but I mean, it was intuitive to the I mean, physicist or philosopher that the difference must be equal to something, and then something was something was called as internal energy. The dq and dw, the difference of dq and dw was a mystery for a long time, but they introduced this term du. So we say that first law gives the definition of internal energy. So that is the purpose of first law. Every law has come to define something in physics. So first law actually came to define the internal energy. Second law came to define the entropy. The zeroth law came to define the temperature. And again, there's a history why it is called zeroth law, right? And the third law of thermodynamics came to define the absolute temperature. Sorry, absolute zero. So, okay, this was a simple application of the cyclic process relation. For any cyclic process, the du is always 0. So based on that also can define something. Anyway, now we can enter the world of thermodynamic process. So anyway, I'll mention this point. First law gave definition of internal energy. I mean, historically, you should know this. I mean, it doesn't matter whether you know or not. Anyway, let's define the types of thermodynamic process. So the famous one, the first is called isobaric process. Second is isoporic process. So iso means same. So isobaric means same pressure. Isoporic means
Same volume.
constant pressure. Isoporic is constant volume, right? The third is what?
Isothermal.
Very good. So what is the isothermal process? So after this,
Adiabatic.
so adiabatic process means no heat transfer. System cannot undergo heat transfer. Does it mean it cannot undergo energy transfer?
No.
Correct. So it can still have energy through which transfer?
Work transfer.
Work transfer. Very good. So then we have many more transfers, but the famous one is called
Polytropic.
polytropic process. So what is polytropic process?
PV to the power K is equal to constant.
But what is the process? That is the relation of the process. Can we say every other process other than the first four is polytropic? Tell me guys, can we say that any process other than the first four is polytropic?
Yes, sir.
So you must have heard this in chemistry, right?
Yes.
Very good. So half of the world population doesn't know. Very bad. Anyway, so a process in which the molar heat capacity remains constant is called polytropic. So not all processes are polytropic. Anyway. So the next we can say isenthalpic process. So the name says the process in which the enthalpy remains constant. So isen, basically what you're writing is iso plus enthalpy. So because there are two vowels, what we do? The first vowel gets cancelled. So the name becomes isenthalpy, right? This is how you study the organic chemistry nomenclature, right? Anyway. So whenever you add two words in which the ending and the beginning is vowel, we ignore the first vowel and we continue with the second vowel, right? So constant enthalpy process. So we say H is constant. And what is the definition of H? It is U plus PV, right? So we'll come to that. Similarly, we have isentropic process. So here the entropy is constant. So we can say the ds is 0. This is the change in entropy. And later on, you will come to know that the ds is actually dq by t. For a reversible cyclic process, we write this way. So if ds is 0 implies what? dq must be 0. See, if ds is 0, can we say ds is dq by t? So ds is only 0 when dq is 0, isn't it?
Yes, sir.
Yes.
So basically, isentropic process is actually the another name of adiabatic process. So it is also adiabatic process. Okay. Now you can define, of course, the other name, like cyclic process. So cyclic means initial state equals to. So for any cyclic process, dq du will be how much? 0. The ninth is, of course, we can say quasi. So in fact, every process which is thermodynamic is by default quasi-static process. A process is said to be quasi-static if every change happens in elementary form. For example, if I give you a bucket, okay, so let's say you're taking a bath with a bucket and you take the entire bucket and pour on yourself. So the transfer of you can say water as energy. So the transfer of energy was in elementary step or in bulk state. Bulk state. If you pour the entire bucket, can we say it's a bulk process? It
Yes.
happened at once. Now, if I give you a tiny spoon, so you're supposed to take the spoon inside the bucket and throw it out. Now, no matter how fast or how slow you throw the water coming out will be in elementary step, isn't it? Hello, hello.
Yes, sir.
Yes, sir.
So when things changes in elementary step, then at every step things will be in equilibrium because changes are very small. So a quasi-static process is when any process which take place in elementary step, that's it. So any process which takes place in elementary step. So in fact, every process that we are studying is all are quasi-static. So isobaric is also quasi-static, isochloric is quasi-static. Everything is quasi. Quasi means almost. Static means almost at rest, but it is, I mean, the change which is so slow, which looks like, which perceived as there is no change, but there is a change, we call quasi-static. Other name? Reversible and so what is the reversible process? So if a process is reversible, then
On reversing the conditions, we can retrace the original path.
correct. So every reversal process must be quasi-static. And therefore, if you change the state, it will just trace the same path as you came through. So a reversal, if a process is reversible and cyclic, then you will not see two paths, you will see the same path getting retraced again and again. And therefore, it is a very famous question that in a reversible cyclic process, the work done will be how much? And the answer is 0. Because the forward path is same as the backward path, so area under the curve is plus and minus equal value, isn't it? So if you go by the path and you come by the same path, the area under the PV graph is how much? For the
Zero.
upward journey, it is positive. For the downward journey, it is negative. So then it is,
Mhm.
do you realize this? Or you can say what is the area of the loop form? It is 0. Here the loop is forming 0 area, isn't it? It's
Yes.
the same line. You're tracing the same line twice. So the area of the loop is 0. So in a reversible cyclic process, the work is always 0 if it is reversible and cyclic. So for irreversible process, the path cannot be same. So if you go from one state to another state via path 1, and if the process is irreversible, can you come by the same path? But if I draw the irreversible process, and even though it is cyclic, you may go through A to B via path, but you can't come back via the same path. The path will change. So you won't be lucky enough to retrace those points which you traveled in while coming A to B. So of course, this process is any other process. Can you tell me? Am I missing something? I mean, there maybe must be more. So if you know any other process, just let me know.
So,
Yeah.
sir, comparing quasi-static process and thermodynamic process.
No. A process is thermodynamic only when it is quasi-static. So that is like the base of every process. If a process is thermodynamic, it must be
Quasi-static.
yeah, you cannot stop it. Okay.
Okay, sir.
I think, I mean, of course, there must be more. So we have isentropic, adiabatic. Let's call ETC because I don't. Oh, I can't recall many more. Actually, there are many more. I mean, it's a long time. I will need to revisit. So these are the processes. I mean, it's more than sufficient for JEE part. So let's start with each process one by one. Now I'll tell you how we are going to study. See, every process will have 3 parts. A process, you're going to learn every process. Then you will have 3 types of calculation: DQ, DW, DU. And you will have graphs. So you have to deal with the 2 types of question. One is numerical calculation, then the graphical question. And the same is true for all types of problems. So we have to do all these three calculations. So every question that you are coming across, you have to answer certain things. Before we start solving problem, we need to understand something called sign convention. So sign convention of DQ. So we are trying to, drive the system, and we promise to provide what? Heat. Because the sole purpose of a thermodynamic engine is to convert heat into mechanical work, isn't it? So you buy a car to convert the fuel into mechanical work, which will drive the chain, the belt, the wheel, and so it will run on the road, isn't it? Hello.
Yes, sir.
Yes, sir.
So what is like when you're happy? I mean, when you're giving heat to your engine, so that should be taken as positive or negative?
Positive, sir.
Very good. Because you have to give, then only the work you can expect. So energy received or absorbed by system we take as positive. So when you're doing a calculation and it turns out to be DQ is positive, it means that much energy is absorbed by the system. So positive means heat is absorbed by it's clear. And if DQ is negative, it means heat is released by the system. Is this clear?
Yes, sir.
So what about the sign? What about the sign convention of DU? If DU is positive, what does it mean?
System has
Its
gained.
temperature has increased. That's it.
Yeah.
Because the U depends on temperature, nothing else. So to understand whether the DU is increasing or decreasing or is constant, just think about the temperature, nothing else you have to think about. So if DU is positive, it means temperature of system has increased. And negative means he has decreased. And the sign convention of DW we have discussed already. So once again, sign of. So if work is positive, it means the gas has lost, the system has given that energy to its surrounding. That's it, right? So positive is what? You have worked on someone, so you have given that energy to someone, right? So that much energy has gone away from the system, can we say?
Yes, sir.
If DW is positive, we can only say it's expansion. And so in this case, what we can say? Energy is, work transfer. Work transfer work transfer, what we can say has occurred. Work transfer is okay. Leave it. I will do that. If dW is negative, then so a positive work means you have consumed, the system has consumed energy from its either saving or from its receiving or from both also. So let's say if you do 100 joule work, you receive 50 joule work. So 50 you receive and 100 you, 100 you consumed. So from where the 50 must have come? So the rest 50 will come from the loss of internal energy of system. The system must have lost 50 as well. It means such system must undergo cooling process. Understood what I'm saying?
Yes, sir.
So when a system is suddenly, kind of expanded, it cools down. So it happens it cools down. Okay, so these are convention you should be aware of. That's it. Let's do the. Now these are the standard questions will have standard answer, and one should know the answer also. So we'll start with the first process. Isobaric process. So for isobaric process, P is constant. Okay. The first question is, when you know that P is constant, then how to get the equation of path? How to get the guiding equation? The equation of path is also called guiding equation. So we know that if a system is at equilibrium, then which equation is always true? So we have the ideal gas equation is always true. IG. And ideal gas equation says PV equals to nRT. If I say P is constant, then what you can add? V equals to nR by P into T, and because N is constant, R constant, P constant, so can we say V proportional to T? Right? And if V is proportional to T, so we can say V by T is constant. Tell me, guys. So which law we call this? This law is called
Charles law.
The Charles law.
yes. So in its journey, when you go from one state to another state through infinite intermediate state, at any instant the V1 by T1 at one state and V2 by T2 at another state, this relation will hold true all the time. And therefore this is called it will guide the path. Now the question is, sir, what is the purpose of a guiding equation? When we should think about it, when we should use it? So if you have, if you go from one state to another state following this process, and if you know the coordinate of the first process, the first state, and in the second state, one of the coordinate and there is something unknown. Let's say V1, T1, and if you know V2, but you don't know T2. You're not supposed to write the PV question twice and then solve. Because this guiding equation is there, just write it between these two states, and because this must be true, the ratio must be same everywhere. So you can compare V1 T1 by V2 T2, and this will give you the unknown value. So that is the purpose of using the equation of state. Of course, to write the equation of state, it must be some thermodynamic process. So every thermodynamic process will have this equation of state, this guiding equation. Okay. I hope this is clear.
Yes, sir.
The first part. Okay, so after writing all this thing, I'll show you okay what kind of analysis we do generally. So the first part is like you calculate three things. You calculate work, you calculate DW, DQ. So all three things you calculate. Now this process is so famous that DQ we can directly write as. Okay, I'll start with the DW first. So DW we can write as here what? The definition is PdV. Correct?
Yeah.
And because it's a PdV, so okay, we can live like this. But in this particular case, PV equals to N0. P is constant. Can we differentiate both sides? If I differentiate both sides, what I can get? PdV equals to NR dt, isn't it?
Yeah.
And that is why the work done in this particular process, we can write either in terms of volume change or in terms of pressure change, I mean temperature change, both are equally valid. So PdV you can replace by NR dt, and that is the beauty of this process. So you have two options. If you know the temperature of the end and beginning, you can find the work. I will not integrate. I mean, if only when we know the answer T2, T1, you can convert accordingly as per the question. So first step is done. We know how to write the work. The second is what? How to write the du. Now du, to write du, I do not need any process. I know the formula. It's NCV dt. So this is again done. So the second part is also done. First part is done. Now dq is always defined as the sum of the two. So du plus dw. So if you do not know anything about dq, just find du and dw because these are easy to find and add them together, we get the dq. But in this process, we know the answer. What we know? It is isobaric. So the direct answer we can also write. And you can see something. I can take n dt common. What I'll get? Cv plus r.
Yeah.
And we know C plus R is
CP.
C. So I could have written that directly, but anyway, I just wanted to show you that okay, you can always choose the summation method because that's generally easy to solve. Directly finding dq is a challenging task. I'll tell you when to solve directly. But anyway, the answer comes n Cp dt, which you could have written directly also because the process is very much well defined, known to us. We could have used that tradition directly. So is this clear to all of you? So 3 step is done, the du, dw, dq. Now, what they will ask you next? So once you're done with the process, the calculation, the guiding equation, the next thing that you should remember is called graph, which means indicator. So here P is constant. So which graph is meaningless? PV graph is meaningless, right? It's meaningless means it's very easy to plot actually. And PT graph is also easy to plot, isn't it?
Yeah.
If you plot PV, I mean PV, PT, in both cases the equation is straight line. So that's why I'm saying such kind of graph is meaningless. Why we should plot this? So in every graphical question, we always look for the graph which is difficult because that will be asked to you. So which graph you have to plot here? So you can always check the guiding equation and you will come to know which graph is required. So we must plot the VT graph.
Yeah.
And the equation is V equals to CT, I mean C means constant. So a graph Y equals to MX will pass through origin, isn't it? Hello, hello.
Yeah. Yes.
But we cannot draw from origin because zero volume is not possible. So we can draw by dotted line first and then make a board line. This is a typical convention. So what is the slope representing? What is tan theta?
V by T.
So tan theta is how much? It is NR by P. Do you realize this?
Yes.
So slope is here. And now this is the crucial part. Slope is going to be inversely proportional to pressure. So a
Yeah.
high pressure system will have lesser slope in VT graph.
Yeah.
So this is very typical. I mean, I hope you have done this before. So if I draw more number of such graph, but of course for different system, not for the same system. And if I give you the arrow, if the first graph is plotted for P1 pressure, second for P2, third for P3. So can we relate the pressure here?
Yes.
So this will help you in relating the pressure. So more the pressure, more lesser the slope. It's less steep. So which one is biggest pressure?
P-
I think very typical question you must have done before. Okay.
Yes, sir.
Now comes the really interesting part. In this particular isobaric, we have many interesting things we can discuss about. The relation of dW, dQ, or du, all are interrelated. In fact, I can express every answer in terms of dW, which means if I know the work, I do not need any other value, any other calculation. I can do it easily. So dQ is how much? It is NCPDT, right?
Yes.
Okay, let's write everything in terms of temperature. So this is NRDT. NCP. What is CP, guys? If you remember, CP is gamma R by gamma minus 1. If you remember, we have done this before.
Yeah.
Yes, sir.
So it is like gamma upon gamma minus 1 into NRDT.
DW.
Basically, if you know the gamma, you can get the dW dQ directly. In fact, sometimes they will ask you, can you find the ratio of and the ratio doesn't depend on the anything. I mean, it depends on the degree of freedom only, or the gamma value. What is gamma? What the gamma is called?
Diabetic.
What do you call gamma? So the name for gamma is? I hope you all have studied in already this in chemistry, right? What is gamma called?
Adiabatic exponent.
Very good. So we call adiabatic exponent, and gamma is how much? 1 plus 2 by degree freedom. So if you know the nature of gas, the ratio can be determined, right? And you're going to get question of this nature, I can guarantee. Similar du we can attach NCV dt, which is NR dt by gamma minus 1, which simply means dW by. It's so simple. So du by dW is how much? So if you know one value, if you know gamma, you can relate anything, whatever you want. And this question is again typical of JEE-Mains and advanced both. So having, I mean, this correlation is really important for you. I mean, you can use it direct. And why it is interesting? I'll give you again one example. See how interesting the question can be. So I'll give you one graph. Simple. So definitely I'll give you some nice values, V naught, 2 V naught, P naught, 3P not whatever I oh, what I'm doing. Just a minute. So the graph will be like given to you like this. So first of all, you need to identify this. So first difficulty is when you see VT graph and the graph is passing through the origin, you must realize this is which process?
Yes.
So here, if you pass, then you can solve this question. So do I need to give this volume? This volume must be how much? If V naught is given, T naught is given, and if I say this is 3 T naught, this will be how much?
Even
I mean, in fact, even it is not given, you know this is the answer. And there's nothing rocket science here. So, okay. The area will have no meaning here. But you realize that this process is what?
Isobaric.
This is isobaric. So if I say the number of moles is 2 moles, the gas is monoatomic gas. So the moment I say all these things, okay, what is easy to determine here for the given process? Process A to B. Which quantity you can determine just like this at one go?
TW.
Is it PV graph? What is known to you here? You know the temperature of the initial state and the final state. And if you know the temperature of initial and final, which quantity we can determine quickly? So which thermodynamic quantity only depends on temperature?
internal energy.
So you must realize that you have to find the du quickly as possible. If you realize this part, then only you can solve question fast. So you must calculate du first. Whatever you find convenient, do it at one. So du is how much? NCV dt. And dt is how much?
2T naught.
So dt is 2T naught here. So my job is done. Because I got the du. I can find any other answer, isn't it?
Yeah.
So I need to do the calculation, in fact. So I know this relation. I know this relation. So I can find the dw must be how much? The work is how much? It is gamma minus 1 into du, right?
Yeah.
And gamma, I know gamma. So I'll keep it like this one. I mean, there is no need to do. The CV is how much? R upon gamma minus 1. So this gets cancelled. And mole is given to you how much? 2 moles. So answer is 4R. So of course, at the end you can decide 4RT. So for this question, the work is how much? 4R T naught. So for every graph, don't find the area. Area is only good for the PV graph. What is the meaning of area of VT graph? It is integration of V dt, right? And V dt will make no sense to you, right? So when you see a graph, you spend at least 30 seconds in thinking, first of all, which graph is given to you, which quantity can be determined easily. Sometimes you will see the work is easy, sometimes you will see the temperature is easy. Every time you will see something. And you develop this, way to look at in a broader picture, what is given, what we should start with. And then you will enjoy the thermodynamics. Else you'll find it cumbersome because you will fail to realize that how to proceed, because there are so many relations. These tiny relations will disturb you. I hope this is clear.
Yes, sir.
Yes, sir.
And you can also find the DQ. And again, I can use directly NCP DT because DT is known to me, no? So I'll just directly use and we'll get the answer. And because I know the DQ, I know the DU, I can subtract also. So it is up to you to, develop the proficiency of manipulating this equation. As a beginner, the biggest challenge to master the thermodynamics is the ability to manipulate so many small things. So when you start solving, give some time, solve. It won't be difficult after some time if you have the open perspective of looking at things and the realizing what is good for you. Okay. Sometimes I also get stuck. So I spend time thinking, okay, instead of throwing myself blindly to apply the formula, I spend some time thinking that can we do it easy? Okay. And I have realized that whenever I have thought about for some time, I have always got a alternative way of solving, which is really fast and effective. That comes only through the experience. So when you solve more questions, you will get more experience. So this was all about the isobaric process. You've done the graph and so on and so on. Okay. So which process we should go next? The second is
Isochronic.
so this is a process of no use because it's not going to do any work. So as an engineer, we are not going to use the volume is constant. So what cannot happen here?
Work done.
So work is not going to happen. It means one of the calculation is gone, right? And when you have out of three variables, if you have one variable 0, the other two are equal and opposite, kind of, right? Or equal values.
Yeah.
So your duty will reduce drastically. I mean, because dw is 0, and we know dq is dw plus du, and this is 0. So dq calculation is same as du calculation, and du is known to everyone. It is NCVDT. So my job is done. So I have done all three calculations. Okay. But what is important here in isochoric process? The ability to plot the graph. So because V is constant, so if I use the ideal gas equation and V turns out to be constant, so I'll separate the all constant in one side. So you get the PT relation, right? So P by T is constant. And we can directly add what is slope here?
And R by.
So which law we call? This P by T constant? So P1 by T2, P1 by T1 is P2 by T2. Which law we call this? It's the Gall-Lussac law, right?
Yes.
Now let's plot the graph. Which graph we will be plotting here?
Volume versus.
No, see, volume is constant, so why will plot? It's a simple line. Plot the PT graph because here V is missing, right?
Yeah.
And we know P and T relation. It is Y equals to mx. So again, it is equation passing through origin. And if I draw many such equation, sorry, many such lines. Let's say all are expand. Going this way. So can you relate the volume of V1, V2, V3?
Yes, sir.
What?
V3, V2, V1. Decrease.
Okay, so we have done all the values. We know the ideal gas equation. We know the guiding equation. We know the volume relation. And this is done. No need to worry much. This is the easiest process. So let's go to the next process quickly. And always see, in every process, there is one particular thing which is difficult, and that you will, you will be asked actually in the examination. So the third is isothermal. So in nature, the isothermal process, we know every melting action or every vaporization action, these are isothermal in nature, right? For gaseous system, creating an isothermal process, of course, the phase change of matter is isothermal, the temperature remains constant. But for gaseous system, the isothermal process is highly impractical process. So, which means in real life, we cannot achieve this process for gaseous system. Although it is happening, of course, it is part of thermodynamics, and you will come across later on in the second law that because of this particular isothermal process, Carnot failed to create a real engine. So he only formulated the hypothetical engine with best possible efficiency, but that cannot be realized. So later on, Rudolf Diesel and Otto, I think Otto Hahn only, they designed a modified Carnot engine, which actually worked, and the world got the real engines, the practical, usable engines. Okay. So Carnot engine is like the, you can say, the Mona Lisa of Leonardo DiCaprio. What do you call it? Mona Lisa is Da Vinci. Okay. You can say. So that is this Mona Lisa of Da Vinci. It's not real. You know, the Mona Lisa is equation of mathematics. Okay. Put into some shape, which we called a Mona Lisa. Mona Lisa is neither male nor female. It's just a piece of art. Carnot cycle is similar. It is the Mona Lisa of Sadi Carnot. We design an engine which cannot be realized ever. So in isothermal process, the temperature is going to be constant. And the moment you say temperature is constant, the dT will be 0. And the moment you say dT 0, the du will be
0.
So any process which is isothermal, the internal energy change cannot take place, which means if you give some energy to the system, if you give heat to the system, it has to work completely. 100% efficient. Is it possible in real life to have someone 100% efficient? You give money and 100% is converted into work without any loss.
No, sir.
So the real life, it is like a very ideal guy. This process is very ideal in nature. It says that if you do some work as per the isothermal process, whatever energy you give, it will be converted into 100% work. So if it is like, if I slap you, you should not feel the pain. Then how I must slap? The answer is you should not slap, right? Because when you slap, then pain will be there. So it is like I am giving heat to someone and the temperature should not change. So you must give the heat dq in infinite time such that it is consumed into work and will not affect the temperature. I mean, it is like highly impractical. You can understand or relate as well. So for any isothermal process, one thing is gone. Du is 0. So which other two calculations you are going to get here?
dW and dQ.
dW and
dQ.
dQ. Now, which process is, I mean, which calculation is easy here? Calculation of dW or calculation of dQ?
DQ.
How?
Oh, sorry, DW.
So here the dW is feasible. So anyway, first of all, write the ideal gas equation. PV equals to everything is constant on the right hand side. So P and V relation is well defined because the numerator is constant, so it is nRT by V. And because we know the P as a function of V itself, because this is constant, the integration of P dV is going to be easy task, right? So in case of isothermal process, the only thing is the work is interesting. So work is P dV. Luckily, we know P in terms of V. And let's say you integrate from V1 to V2, so you know the answer. nRT is constant, we can take it out. And dV by V becomes ln. Whenever you see the term log ln in work, you can directly say it must be isothermal process. And the answer is well defined. W equals to nRT ln V2 by V1. And because we know P1 V1 is equals to P2 V2, which equation, which law this is called?
Boils.
So the Robert Boyle, in his honor, we call Boyle's law. And from here, the ratio of V2 by V1, we can also write as P1 by P2. And that's logical. As volume will increase, pressure will decrease, right? So it's inverse relation. So the work can be expressed also in terms of W nRT ln P1 by. So these two formula are important for this process, nothing else. And there is no need to think about the dq because the dq is same as
GW.
So in isothermal process, we always calculate the dw, which is always the log relation, and dq will be equal to dw. No need to do the separate calculation. I hope this is clear.
Yes, sir.
Now, as the volume will increase, the work will be positive or negative. So work will be positive,
Yeah, expansion.
and dq will be also positive,
Yes.
which means energy heat will be absorbed by the system.
Yeah.
So in isothermal process, when there is a heat absorption, it will expand, and when there is a heat release, it will shrink. Okay. So isothermal can be of two types. You can say isothermal expansion, isothermal compression. In isothermal expansion, heat is absorbed by the system. In isothermal compression, heat is released by the system. It is clear.
Yes,
Yes.
sir.
Now the graph is very much simple. So let's talk about the indicator diagram. See, if you spend some time in realizing the process, I mean, the significance of the process, probably you will not struggle with the substitution. You know, okay, this process is, this is happening, this will happen, I have to write this and this thing. This. Okay. So the indicator diagram is pretty much simple, PV equals to constant. So here, which graph is interesting? See, temperature is constant. So we should plot which graph?
P versus.
PV only, right?
Yeah.
And this is called the rectangular hyperbola, right? If you remember the mathematics. If I draw many such lines, it is called isobars, right? So can you guess which temperature is higher? And how you're going to guess? So temperature is nothing but the product of PV proportional to this, right?
But T1, T2, T3 degrees.
So which one is biggest?
T1.
Very good. So whenever you get confusion, you can draw either horizontal and now vertical line. So horizontal means P is fixed. So as volume will grow, T will grow, right? Or you can do the vertical line test. If you keep the V constant, then as pressure will rise, temperature will rise. In both ways, you can get the answer. Okay. Now comes the slope part. So PV is nRT, which is constant. So to find the PV slope, you can write the fractional differential dP by P plus dV by V equals to 0. So dP by dV is how much? So slope of isothermal is minus P by V, right? And the negative is saying that it is obtuse angle. If you draw a tangent to the graph, it will be always obtuse, isn't it?
Yes, sir.
So it depends on the ratio of P and V. So as the ratio will increase, it is more. That's simple. All right. I hope this is clear to all of you. The graph part.
Yes.
Yes.
So let me give you one or two questions based on this process. Let's say this is PT graph or maybe PV graph. So let's say this is PT graph. So how this process will look like? A vertical line.
Isothermal.
Because temperature is constant, no?
Yes.
Can you tell me what is the work done in this process? So work done we can write as
nRT ln 1/2.
it is P1 by 2, so it's 1 by 2. And the answer is negative, right? So in the process A to B, the heat is released. I mean, sorry, work is negative means what? The dQ is also negative. So system is releasing the heat to the surrounding. Or you can
Yes.
say the system is getting compressed, right?
Yes.
Someone is compressing it. And that is why the pressure is increasing, right? So you know this answer, and how easy is this? Similarly, I can give you this question and you can answer like this. So if I give you VT graph, a similar question. And if I draw an arrow like this, so what is the work in here?
nRT not ln 2.
But this case it is positive, right?
Yes, sir.
So work is positive, so dQ is positive, which means heat is absorbed in
Absorbed.
this process. Right, guys?
Yes.
Okay, so these are some typical questions that you will come across. Okay, the next is which process?
Adiabatic.
So in the adiabatic process, what is there? dQ equals to 0. Now, if you say that dQ 0, can I use the ideal gas equation to derive the guiding equation? So you are saying that dQ 0. So can we get the ideal gas equation for the? Can we use the ideal gas equation for deriving the guiding equation? Can you find the PV-T relation? Yes or no?
Can you repeat?
So far, you got the relation PT, PVT, PV, right?
Yes.
because it was given that one of them is constant.
Yeah. So
And
we
PV
can't
question
find then
PV question was having 3 variables. If you make one constant, it will give you a direct
two value. Yeah.
relation. But how to get the equation in adiabatic process? So here you cannot derive it directly from the ideal gas. You have to derive from the scratch, from the first law definition. So dq is 0, and from the first law we know dq equals to,
du plus 2
and du is like universal.
in singularity.
This is pdv, right? We are going to nr dt by gamma minus 1. Okay, so again I have p, v, and t. So I can see all 3 variables in the same equation. So any differential equation we can only solve if it is in 2 variable, right? Because
Yes.
if you do the variable separable, then it should be only of 2 types, right? The problem here is I have 3 types of variable. So again, it's a very logical step. What is the third way? I mean, how to eliminate the one of the variable? So for that, we have to use the,
Ideal gas equation, sir.
so we will add PV equals to nRT. And to get the differential relation, you can add dP by P, d by V equals to nR is constant, so dt by. It is up to you to choose whatever. Like what you want to replace, you can replace from here. So what you want to replace? PdV, VDT, what you want to replace? Like which 2
Yes,
variable
sir.
you want? You want P and V relation?
Yes.
So let's replace T dt. So dt we can attach T times. So this equation 1 and this equation 2, use it. Let's do that. So it is up to you. Whatever you want to replace, you can replace from 1 and 2. So what we can add? 0 equals to n r by gamma minus 1. And dt we can attach T times what? dP by P plus PdV, right?
Yes, sir.
But okay, the differential is now into 2 variable, but the variable the t is there, but that's not a problem because nRT becomes PV from the ideal gas equation, right? So no need to worry, right? So what we're going to get here, dP by P plus and nRT can be replaced by PV. Tell me guys, yes or no?
Yes, sir.
So now we have PV upon gamma minus 1, then dP by P plus d by V. Of course, you can multiply PV inside. And I think, okay, just simply okay, I'll add it on next page. So PV into dP by V. So this is VdP plus PdV, right?
Yeah.
And I think we can rearrange the PdV term. So it is VdP upon gamma minus 1 plus PdV take common. What we are getting? 1 plus 1 by like something like this. So what you are going to get here is VdP plus PdV gamma upon gamma minus 1, right? This is okay. So now finally we got the answer. VdP plus PdV into gamma is 0. And this is PT. So PdV, I mean, unnecessary, but you can divide by PV both sides. And now this is perfectly rearrange variables. You can integrate both sides. It will become ln p plus gamma ln v is equals to constant plus anything constant is constant. So you can say let's call ln c, and so we get ln pv power gamma equals to ln c, and therefore now we have the relation. So here the guiding equation comes through the derivation, right? So this is your because as I said that nothing is constant here, so we will get C guiding equation because you wanted to derive in terms of P and V first, so you got PV. Next, there is no need to derive. Replace one of them by ideal gas equation relation. So if I want to add the T and V relation, for T and V, what to connect? Replace P. So PV equals to nRT. So P is how much? T by V. And anything constant will go on the other side, will remain constant. So I'm writing this way only. So this will become TV power and the last relation is, so if JEE-Mains advanced, whatever, if they will ask from the adiabatic process, then these equations will be useful to you. So for P and T and P relation, keep the pressure, replace the volume. So P and V per gamma. V we can write as like this, guys. Tell me, is this clear? Why I'm writing? The
Yes,
way I'm
sir.
writing?
Yes, sir.
And now this will become T per gamma upon P per gamma minus 1 equals to constant. So you may write I mean, there are many ways of writing. You can write T proportional to P per gamma minus 1 by gamma or P proportional to T per gamma by gamma minus 1. I mean, these all are ways of writing. And therefore, at last, I will write all the guiding equation. So you'll get nice power, nice values. So P1 V1 power gamma is P2. T1 V1 power gamma minus 1 is T2 V2. And I mean, there are many ways for. So for pressure, we can say T1 by T2 is P1 by P2 power gamma minus 1 by gamma, or P1 by P2 is P1 by T2 power. So these are the set of equations that you have to manipulate, use, and do whatever. So they will give you the T1, T2 in terms of nice values, maybe 100 and 200 or 300 and 600. Gamma, they may give you 5 by 3 or 4 by 3 or 7 by 5, depending on mono, di, and polyatomic. And you have to use this relation. Is this clear to all of you guys?
Yes, sir.
So one more thing that they will ask you. So something will be unknown, and I mean, they will, I mean, definitely ask you that use this relation to find the unknown state value or state coordinate. Now let's talk about the slope of PV graph for a diabetic process. Okay. So now we know the answer. dP by P plus gamma dV by V is 0. So if you find the dP by dV, what you get? Minus gamma P by V. Earlier it was minus P by V for which process? isothermal, right? But now gamma has come here. So can we say that something it is interesting? Well, like this. This is important for you. Slope of adiabatic process is gamma times slope of isothermal. Can we say this, guys? Tell me yes or no.
Yes, sir.
Can we say this?
Yes, sir.
Okay. So this is the very famous relation that if you want to compare isothermal and adiabatic in the same graph, then the adiabatic must be having greater slope, more steeper. This parallel comparison is very typical and you will come across. So let's say I draw a PV graph and I draw two lines. So you go 1 to 2 and other goes 1 to 2 dash. Now here we have ADIA and one of them is ISO. And you are supposed to guess which path is ADIA and which path is ISO. One of them is definitely ISO, one of them is adiabatic. I mean adiabatic. It's a both process we are drawing for the same gas.
The second is adiabatic.
So 1 2 dash is
Adiabatic.
Adiabatic, sir.
very good. So now you know this is greater slope, but this is ADIA. This is ISO. You will come across this question, and these all are very typical question that you are supposed to know, in fact. So we are going to compare ADIA versus ADIA. So when you try to compare ADIA versus ADIA, you have to check for the gamma value, right? So both are adiabatic. Let's say we have oxygen and helium. Both are adiabatic. Can you guess which path is adiabatic, which path is oxygen, which is helium? Tell me. So which path is helium, which path is meant for oxygen? Both are adiabatic.
Sir, 1 2 dash is oxygen.
So gamma is okay. When you have the both adiabatic, then you have to compare the gamma because more the gamma, more the slope.
Yes.
So which one is having more gamma? Monatomic or diatomic? So gamma for the mono is
5/3,
and di is
7/5.
so this is helium. So which number is bigger? 5/3 or 7/5? If you know
5/3.
mathematics. So mono will be
0.6.
more, right? So 1 to 2
Yes.
dash is
Helium.
Yes.
and this is.
Oxygen.
Is this clear, guys? Tell me yes or no.
Yes, sir.
Yes.
One more thing you can check in the above graph. If the beginning and the end is having same volume, if your gas expands in via two process, both goes from V1 to V2, in which case the work done is more. ISO or ADIA? In a PV graph, how we check the work done? On a PV graph, we check the area under the curve. Hello, guys.
Yes, sir.
Yeah.
So if you look at the top graph, then which process will have more work?
ISO, sir.
Is this clear to all of you guys?
Yes, sir.
Yeah.
More radial. So if a gas is undergoing expansion between two fixed volumes, V1 to V2, one via ISO, other via adiabatic, in which case it will have more work done. So in ISO, the work will be
More.
More, sir.
so it's very interesting. The expansion is same, still the work is more, isn't it? And graphical questions and graphical answers are very important in thermodynamics. And all examples which I'm giving are very standard examples. I mean, this is not, I mean, a regular problem. It is like you need to know these things to solve other questions. So take every question I'm solving as the standard. These are the de facto questions, which will help you in solving other questions with ease. So work done in ISO is more than so work is more. Okay. So what is our next process?
Polytropic.
Now that is the most crucial part. I mean, you need to be very good with the polytropic. You will get many questions on polytropic. Every process which is polytropic, the C must be constant, right? And when C is constant, then definitely it will transform into an equation of the form P power x equals to constant. This you can derive only when C is constant. If C is variable, this formula you cannot derive. I'll show you. So a polytropic will also follow the same formula TB x minus 1 equals to constant, or it is T x. So if you know the answer of adiabatic, you can get the answer for polytropic as well, because the mathematical relation is same, right? Oh, I missed something. Just a moment. I'll come to polytropic in a while. So we got the ideal gas equation. So we got the, I mean, guiding equation for which process? Adiabatic process, right?
Yeah.
But we fail to, I mean, explain other effect, that what is the work done, what is the change in internal energy, and so on. Because dq 0, because dq is already 0, and from the first law says that dq is how much? So this term is 0, so it means these two are interrelated, isn't it? So what you can write? So in case of adiabatic expansion, when a gas expands adiabatically, so when there is a burst of tire burst, or if you prick a balloon, the burst will be random. I mean, sorry, very quick actually. The gas will expand so quickly that it will fail to absorb energy from the atmosphere. So a sudden expansion of gas will undergo loss of its internal energy, as you can see, because I'm not giving you any energy. You want to expand, so what will be consumed? Your own saved energy, isn't it? And that is what formula is saying, that dW is minus du, which means work is done by the gas at the expense of loss of its internal energy. Do you realize this for adiabatic process?
Yes, sir.
Yes, sir.
So can we say because of this particular region, upon expansion, the temperature will fall down? Because internal energy is defined by temperature. So less energy means less temperature. Yes or no? Hello, hello, hello.
Yes, sir.
Yes.
So you all realize that the gas will cool down.
Yes, sir.
So you can take a balloon filled with air and prick it in front of your face. You will see it's a cool air. Okay. Anyone
Yes, sir.
experienced this before? Okay. So we don't keep balloon at home, only during the birthday celebration. Anyway, you can do this experiment at home. Don't try to go near the bus or truck and wait for the tire to burst. Okay, that's very dangerous. But if it happens, then the air is really cool. So this is called adiabatic expansion. Adiabatic compression is also possible. Again, let's try to plot. Okay, now the question is how to find the work done. How to do the calculation of work done. So it is very simple. Because du is universal, we can get the answer directly, right? So we can write NCV dt, guys, right? And CV is R upon gamma minus 1, and dt you can write as T2 minus T1. You can see the work done is how much? See, dt always means final minus initial. Don't write the value wise. You have to write final minus initial, which could be negative, positive, or whatever. So this becomes eventually nRT1 minus nRT2. And from the ideal gas equation, nRT1 is P1 V1, and this
Yes.
is P2. So this is the answer. For if you know the PV, you can express this way. If you know the temperature, you can write this way. So it is your choice. In adiabatic process, the work is very interesting because it's difficult for many students to remember. But if you remember that a formula can give you answer directly. Okay. I hope this is clear, guys.
Yes,
Yes.
sir.
Sir.
Let's say you are not interested in this method. You can say work equals to PD, right? And we know PV per gamma equals to constant. So we can write C by V per gamma equals to. I mean, we can replace like this, right? And we can integrate from V1 to V2. So dV by V per gamma minus gamma. You know how to integrate? How much? The power rule. Is this clear, guys?
Yes, sir.
And now here is the trick part. So C is actually PE per gamma, right? So for the first term, I can replace C by P1 Vin gamma. But for the second term, I will replace C by P2 V2 per gamma. Now this is the trick part. I mean, this is how we derive. And now you can see the answer is. Is this clear, guys? How we have done this?
Yes.
Yes.
So this is the trick part. So I substitute the C as per my convenience to get the nice answer. Okay. So that's from the adiabatic process. One more thing I would like to discuss. Okay, so in the first case, we know the adiabatic is the below one. Correct? In the
Yes.
second case, which one is adiabatic?
The upper one, sir.
Upper one.
I hope this is clear.
Yes.
So that's all about this. One more question is very interesting from graph. Before I enter the polytropic, I will just finish this graph. This is again a typical problem. If I plot a graph, let's say you go from A to B via two process. The same gas goes from A to B via two process. The question is, in which process it will absorb more heat? One or two? Let's say in the process one, it absorbs dq1. In the process two, it absorbs, let's say dq2. So in which process it will absorb more heat?
Sir, DQ1, sir.
Correct. Question is clear? So Q1 is more than Q2, right? So how we decide this answer?
Sir, the change in internal energy is constant, so the measure of work done will give us the relative.
Correct. Very good.
Uh,
So yeah, that's the right answer. So du is same for both, right? Because the endpoints are same. Isn't it? So
Yes.
because you are running between the 2 points, I mean two states, so your the du part is same, I mean same value. Right? Now you have to check the area under the graph because it's PV graph, right? In the PV graph, we must check the area. So area under the first path is much bigger than area under the second path, right?
Yes.
yes, sir.
So more area means more work means more heat absorbed. So I think we are done with the most of the graphical problem from the standard process, the process which are well known to the world. So these are like celebrity process, adiabatic, isochoric, isothermal, isobaric. So from these, you can say celebrity process, we are moving towards those process which fail to become celebrity, but they struggle a lot. And to all those process who struggle but never get the fame, this is the tribute from the physics side. And all those process we call polytropic. So polytropic is to kind of tribute to all process, right? I mean, those who do not become, famous, become stars, but played their role. The name is and what I said, for any polytropic process, the C must be constant. Understood? C must be. What is C here?
Molarity.
Those who became famous are also polytropic. So every star, I mean, of course, let's call it a Bollywood star. Every star is also an actor. But every actor is not an star, right? Isn't it?
Yes.
Yes.
Okay. So how we start with, of course, I'll come across the derivation. But we can ignore the derivation. Every polytropic process will have this format. P power some random constant equals to constant. Or you can write as T minus 1 or T per gamma. Now, if you want to really derive this, you have to start with the again first law of thermodynamics, because we have nothing left here. So what is the first law of thermodynamics? dq equals to du plus dw. And what is the definition of C, guys? Amount of heat required to raise the temperature of 1 mole of substance by 1 degree Celsius.
One.
That was the definition, right?
Yes, sir.
So I can always write dq equals to nc dt, no matter what. But I
Yes.
cannot write CV, CP. No. That is different. That C is for one particular actor, one particular star actually. Okay. So Mannat is only for the Shah Rukh Khan and Galaxy for the Salman Khan. Oh, it's Bangalorean. So those are like famous one. But C without subscript means it belongs to any struggling star. So you can write as NCDT. DU I know. NCVDT. DW I know. EDV. Okay, well, that's good. And again, because you want some relation, you can write something here. NC minus CV into DT equals to VDV. And again, I do not want dt. So what I'll do? As usual, you know what I can do.
Ideal gas.
Now we do not want to, yeah, we have to use the ideal gas equation to replace this differential because we want differential in which two term?
PNV.
P and V, right?
Yes.
So NC minus CV and PV equals to nRT. So PdV plus VdP upon nR is dt. I can add this directly.
Yes.
And NC minus CV upon nR is again a big constant. Oh, this gets cancelled. So what we are left with C minus CV upon R, which is again a new constant. See, unless I will not make C constant, is it possible to treat this as constant? Tell me guys, yes or no?
No, sir.
So now we have this constant PdV plus VdP equals to PdV, and then I can rearrange the PdV term. So C minus CV upon R minus 1 into PdV plus okay, that random thing into VdP equals to 0. I think this is okay to all of you guys.
Yes.
Yes.
And then I'll do the same trick. So VdP plus PdV C minus CV by R minus 1 upon C minus CV by R equals to 0. Okay. So C
Yes.
minus CV, I mean, this is really bad. I can add 1 minus R upon C minus CV. Something really bad. You can see this is. So this entire bad thing, because I don't know whether it's positive, negative, or whatever, it's something X unknown. Let X. So now we have VdP plus PdV into X is 0, right? So dP by P plus X dV by V equals to 0, guys. And now you know how to integrate and get the answer. So it is again ln P plus ln V per X equals to ln C, that's correct. And now you know the answer. Now tell me, the X is a constant, and for X to be constant, what is current condition here? Unless C is not constant, can we call this as constant?
No.
No, sir.
So that is why if you want to create a polytropic process, the C must be constant. Understood? So
Yeah.
if C is variable, then this is not polytropic. This formula is meaningless because X is called polytropic exponent, similar to the adiabatic exponent. So now it is up to you. Do you want me to continue for some more time?
Yes.
Only you want, okay, others are not interested. Tell me, guys. Okay,
Sir.
all right. So join again after 30 seconds because this page is over.